Now that you understand the power of linear regression and gradient descent, you might be thinking that we can solve almost every problem with this technique. However, it is not exactly. So linear regression actually makes a few assumptions in the way it works. So let's quickly take them one by one and understand the underlying assumptions. So the first assumption, which we called out at the start of this module, was that there has to be a linear relationship between dependent and independent variable. If this relationship is non-linear in nature, then linear regression would not give you the right results. So for example, if you are trying to predict a function which has a, let's say, quadratic function like this, your linear regression would try and fit the best line, which would say that there is no variation. So if the underlying relationships are quadratic or they are non-linear, it would not be wise to use linear relationships. In this case, we need to use transformations and transform these functions. So in this particular case, we can transform this using some of these functions like log x or under root of x or even x square in the previous example. So we can use x square transformation here to convert these into linear relationship. I can add another variable y which is equal to x square, and this relationship then turns into a linear relationship. So we can transform these to convert these non-linear relationships into linear relationships and then apply linear regression. The second assumption which linear regression makes is that of correlation between error terms. So it assumes that there is no correlation between error terms. Now, we already know what is correlation. So if two variables are highly correlated, they would impact each other. So change in one variable would impact the other variable. So in this particular case, what do we mean by correlation of error terms? So let's say we create this line, which is our prediction line. The errors which happen in these predictions could be negative or positive. And these errors, which are essentially the difference between the actual value and the prediction, are typically known as residuals. So when you plot these residuals on a chart, there should be no underlying trend in it. So what that means is my previous few values of residuals should not help me predict the next residuals. So in this particular example, it looks fairly random. That is very difficult to use previous residuals to predict the next residuals. On the other hand, if you see residuals to be something like this, I can see there are some underlying trends in these residuals. So I'll need to make some changes in the way I am applying the linear regression. The third assumption is constant variance of error. So if you again plot your residuals, and if you see the variance increasing or decreasing, or if you see a trend in the variance of your residuals, then it violates the assumptions of linear regression. So you should see residuals to be something like these, where your residuals should have constant variance. So you can verify these assumptions by looking at these plots, and if there is assumption which is getting violated, you can use transformations to help improve the performance of your linear models. The next assumption is that of multicollinearity. And again, what it essentially means is that my dependent variables have collinearity or correlation between them. So in this particular example, if I have three independent variables, x1, x2, and x3, I see that x1 and x2 have high correlation between them, whereas x1 and x3 have low correlation. So what this would do is every time I am trying to understand the relationship between y and x1, it will also lead to change in x2. Now you can go ahead and still do your regression and it would give you the results, but your model would become very volatile. So while mathematically your prediction equation might still be fine, but it would change by, if your data changes a little, the equation would change a lot. So hence multicollinearity would still give you predictions, but it will be very difficult to interpret the outcome of the model. So how do you handle multicollinearity? you can actually eliminate one of the variables which is highly correlated. So for example, in this case, x1 and x2 are highly correlated. So we can eliminate one of these variables and refit our model. And in order to do that, one of the ways in which we can do that is by use of parameter VIF. And it is used for diagnosing collinearity or multicollinearity. Now, how do you find VIF? So what we do is we take our independent variables and we build a model where we take one of the independent variables and fit a model from the remaining independent variables to predict that first variable. So in this particular case, if I have, let's say, 9 independent variables, I would take V1 and I would build a model using V2 to V9 which predicts V1. So I'm trying to see if I can predict V1 accurately using V2 to V9, and do I have already enough information to predict V1. And if I get a good model, I would see a high R square. And VIF is nothing but 1 divided by 1 minus R square. So if R square tends towards 1, VIF would end up becoming a huge value. And you typically eliminate any VIF with more than 4 as the value. So VIF can help us address multicollinearity. And the final assumption is that of a normal distribution of errors. So again, linear regression assumes that your errors are normally distributed. So the residuals should be normally distributed. So you can plot these residuals and see whether you see a normal distribution, and you can use the standard QQ chart for this. So if you see most of the residuals coming on these lines within the main quantiles, you would see that this is a normally distributed event. There could be a few outliers, but for most of the curve, it is still normally distributed. Whereas that is not the case, for example, in this chart where you see a lot of outliers and this is not normally distributed. So those are the assumptions which go in linear regressions. In case you see any violations of the results, you would need to use transformations, or you'll need to find different ways to build these predictive models. Thank you.